This is problem number 57 out of the textbook. It says that piles of snow and slippery roofs can become dangerous projectiles as they melt. Consider a chunk of snow at the ridge of a roof with a pitch of 30 degrees. What is the minimum value of the coefficient of static friction that will keep the snow from sliding down? So here is your house, and here is a chunk of snow right up here at the pitch of the roof. Sorry, up at the peak. And we know eventually that it's going to slide down this displacement or the kind of side of the roof here. So the first question is, well, what's the minimum value for the coefficient of static friction that will keep the snow from sliding down? So if I were to draw a free body diagram, I'm going to remember that I need to rotate my coordinate axis. So I'm going to go ahead, oops, and do that and make sure that I show that my coordinate axis has been rotated. And then I'm going to draw in my forces. The weight vector is straight down, but now I realize that I have x and y components of the weight. So I'm going to have mgy acting straight down. I'm going to have mgx acting along the parallel plane. In this case, in the negative x direction. I've got a normal force acting upwards, F sub n, and I have a frictional force, F sub fr, acting up the plane. Technically, sorry, I made a mistake here. This would be the positive x and this would be the negative x-axis. And then this would be the positive y and the negative y. Okay, so now that I've straightened that out, let's go ahead and ask ourselves the usual questions. Is the sum of the forces in the x direction equal to 0? The answer is yes, because the chunk of ice is not moving, and therefore I can say that mgx, which is positive, minus the frictional force, is equal to 0. And then in the y direction, I can ask myself the same question, and I can say that the normal force, which is positive, minus the y component of the weight vector, must be equal to 0. I can see that the normal force is going to be equal to the y component of the weight vector, except I need to remember to use cosine in this case because the angle theta references the y-axis. So now I have an expression for the normal force, which is going to become useful over here in just a minute. On the left-hand side, I get mg times the sine of theta for the x component, minus mu static times the normal force is going to be equal to 0. And now I can kind of substitute this guy in right here in for normal force. If I wanted to, I could kind of add mu static normal force to both sides, which I will. This becomes mg sine theta is equal to mu static, and now I'm going to substitute times mg cosine theta. And now you can see that the mg's appear in each term on both sides. And so this becomes mu static. If I kind of solve for mu static and divide both sides by cosine theta, I get mu static is equal to sine theta over cosine theta is equal to the coefficient of friction. If you don't know that that is tangent theta, which you should, but sine theta is opposite over hypotenuse and cosine theta is adjacent over hypotenuse. When you have a complex fraction like this, you multiply by the reciprocal. This becomes hypotenuse over adjacent. The hypotenuses cancel out, and I'm left with the ratio of opposite to the adjacent side. So the reason that I kind of did this little guy here is to help you remember that sine theta over cosine theta is equal to tan theta. That allows me to solve for theta. Theta then becomes the inverse tangent or the arctangent of the coefficient of static friction, which in this problem was 0.2, and therefore the angle can be resolved in problem number 57. Oh, wait a second, they gave us the angle and we're solving for mu static, so my mistake. So let me get rid of this stuff right here. We don't need all of that. And what I can do is then solve for mu static. It's just the tangent of the angle theta, which was 30 degrees. My mistake. So mu static in this problem for part A is 0.58. Okay, so now I have part A done. Part B then says, assuming that the distance of the chunk to the edge of the roof is 5 meters, and the coefficient is 0.2. So this was the static coefficient of friction. Now we have the kinetic coefficient of 0.2. Calculate the speed of the snow chunk when it slides off the roof. Well, the first thing I have to do is write another dynamics equation and figure out what the acceleration is. Let's go ahead and do that. The only thing that's changed now is that mgx is still here. The normal force is still the same. It hasn't changed at all. The y component of the weight vector, mgy, is still the same, but the frictional force has gotten smaller because we've now switched to the coefficient of kinetic friction, which is always smaller. So now the answer to this question, the sum of the forces in the x direction being equal to 0, the answer to that question is no. And so therefore the right-hand side of my equal sign becomes F net, and I'm going to get mgx minus the frictional force is equal to F net. The sum of the forces in the y direction is still equal to 0, and therefore I can say that the normal force is equal to the y component of the weight vector, or more specifically mg cosine theta, as we already saw up here in the problem. So then I'm going to go ahead and make that substitution. It's going to eventually go here into the frictional force term, but I'm going to be solving for A. This becomes mg times the sine of theta minus mu kinetic times the normal force, but I now know that that is mg cosine theta, and that's all going to be equal to mass times acceleration. So I can see that the mass term cancels out, so the size of the snow chunk doesn't affect its acceleration down the incline, and I can solve for A. Substituting these numbers in for A, I get 5.7 meters per second. It's actually 3.2. 3.2 meters per second squared. I was getting a little ahead of myself. This is not required, and it's not explicitly asked in the problem, but it's kind of an intermediate step. And then now kind of the second part to this is to use kinematics. I'm going to say that the final velocity squared is equal to the initial velocity squared plus 2a delta x, where the initial velocity is 0 because the chunk of ice starts from rest, and I can solve for the final velocity by taking the square root of twice the acceleration times the displacement. When I substitute some numbers in, this becomes 2 times the acceleration of 3.2. I go ahead and put that in meters per second squared. And then I'm going to multiply that by the displacement of 5 meters. And then that's what gives me the final velocity of 5.66 or 5.7 meters per second once I deal with sig figs. The last problem then says, okay, so let's say it gets to the edge of the roof, which is 10 meters above the ground. What is the speed of the snow when it hits the ground? So tricky problem. I'm going to go ahead and move on to another page in order to solve this last part. And so now I kind of have a projectile problem. So here's the edge of the roof. And we should recognize that once it leaves, it's going to kind of do this kind of thing. And we know that the height of the edge of the roof to the ground down here has been given to us as 10 meters. And so they asked for the speed just before impact, or the final velocity right before it hits the snow. So we know the speed right here, the speed we just solved for, it's 5.2, sorry, not 5.2, 5.7, and that is meters per second. But this velocity can be resolved into its x and y components because of this roof angle of 30 degrees. So now I can say that the x component of that vector is going to be equal to v cosine theta, or 5.7 meters per second times the cosine of 30 degrees. And when I do that, I can find that the x component is equal to 4.9 meters per second. Likewise, I can find the y component very similarly by multiplying v times the sine of the angle. I get 5.7 meters per second times the sine of 30 degrees. And when I run that through my calculator, I am getting 2.83 meters per second. So now that I have the x and the y components of velocity, I should recognize that when, if I'm ignoring air resistance, the x component of velocity is not changing. So the x component of velocity when it lands right here is going to be just the same as it was when it started. So we know it's going to be 4.9. But the y component of velocity does change. It's accelerated by gravity. It's initially a downward, or a negative 2.83 meters per second, and it's only going to get larger. So the trick to this problem is finding out like what that y component of velocity is. I can use kinematics for that. I can say that the y velocity right before it hits the ground is going to be the initial y velocity. I'm sorry, the final y velocity squared is going to be equal to the initial y velocity squared plus 2a delta y, where delta y is equal to 10 and a is equal to negative 9.8. And so therefore, the final y velocity just before it hits the ground is going to be equal to negative 2.83 meters per second. And I have to remember to square that. And then I'm going to add to it 2 times negative 9.8 meters per second squared. And I'm going to multiply that by a vertical displacement of negative 10 meters. It's negative 10 because the displacement is in the downward direction. And I can see that the final y velocity in this case is going to be 14.3. Now this is a downwards 14.3 meters per second. So now I know the y component of velocity here. The second part of this problem is basically really just kind of dealing with vector mathematics. And now I can see that this is what I'm looking for, which is really the final velocity. So I'm going to use the Pythagorean theorem for that. If they had asked for velocity, I would have needed to have found the angle, but they didn't. They asked specifically for speed. So I'm going to just use the Pythagorean theorem, or I can say that the final velocity is squared is equal to the y component of velocity squared plus the x component of velocity squared, and so therefore v is equal to the square root of 14.3 meters per second. Now technically that's negative, but it's going to come out in the wash here when I square it. And I'm going to add to that the 4.9 meters per second, which I need to remember to square. And I get a final velocity once I deal with that of about 15 meters per second. So that is the rather lengthy answer to part C of the problem.